All right, page 93 in your textbooks, and you had just one question to answer. That's question 8, and then 2 problems to work. Problem 1 and problem 4 there on page 93. Go and have that homework out so that I can come by and check. Good. Good. And just to throw you off, right? Come to this side. Good. All right, question number 8 asks, what is acceleration? And what did you have, Kendall?
Acceleration is any change in velocity per unit time.
Good. Change in velocity per unit time. Good. Let's go and review some things before we take a look at those problems from last night. Let's go review some things from our last lesson. We began studying motion, which again, to me, I'm like, okay, this is really where physics gets started. I suffered through the first 5 chapters, whatever. Now we get to the real physicsy stuff. And the study of motion is called what, Audrey? Mechanics. Good. So a mechanic is somebody who fixes things that move. Mechanical devices are those devices that have moving parts to them. Mechanics, the study of motion. And we said that as we begin our study of motion, and it's a big unit that has chapters 6 through 13 in it. So it's the largest unit in your textbook. So we're going to start by looking just at the motion itself. We're not really going to care about what caused the motion for now. Michael, what term did we say describes the study of motion with disregard to what causes it? A funny word. Anyone? Kinematics. Kinematics. What is it, Michael?
Kinematics.
Kinematics. Think of kinetic, right? It refers to motion. Kinematics, the study of motion with really disregard to the cause of the motion. And we said that there's different types of motion there. But the type of motion that we're concerned with in this chapter, and really for the first little bit, is motion that results in a change of position. Motion that results in a change of position. What was that term that described motion resulting in a change of position? Kendall? I said, think about Enoch. He was here on earth, and then God took him and he was in heaven, and his position changed. The Bible says he was...
Translation.
There we go, translated. So translational motion is motion that results in a change of position. Now we said translational motion takes an object from one point to some other point. If the object follows a straight line path, that's what we're going to assume. We're talking about what type of translational motion, Audrey? Rectilinear motion. We said if it happens to follow a curved path, Michael, that would be curvilinear motion. But for our purposes, we're assuming a straight line path because mostly our discussion from point A to point B, we're going to be looking at that straight line distance between the 2 points. What is that term for straight line distance between any 2 points? Anyone? Displacement. So we're going to turn non-rectilinear motion into rectilinear motion by ignoring the route that's taken. So if I were to walk to Audrey's desk, I could walk all the way around the room, but as far as physics is concerned, how far apart is my position from hers? Never mind that there's a lectern in the way that might get knocked over, right? Just what's the straight line distance? What's that displacement? And we'll base everything off of that. So we're going to artificially turn things into rectilinear motion. Now we said one of the most important things to study in motion is how fast is something going? And in general, how fast something's going, class, we just call speed, right? What is speed? How do we find speed? Kendall?
Distance divided by time.
Yeah, the distance divided by time. Distance traveled divided by time traveled. Now, technically, if I were to walk to Audrey, I would not go in a straight line because I'd run into the lectern. I probably also wouldn't go all the way around the back of the room unless I just didn't want to walk right in front of the camera, which I already am. But if I were to walk in a curved path, right, I would have to add up the actual total distance traveled, right? And so divided by the total time that it takes to travel, that's distance. Distance, again, doesn't really account for direction or anything like that. So we said that, or speed rather, doesn't really account for direction. So we said speed is what type of quantity? We said our quantities in physics can be broken down into 2 categories. Those that have a magnitude, but not direction, and those that have magnitude and direction. Which one's which? Do you remember, Audrey?
Scalar.
Okay, a scalar is one that has
No direction.
It's directionless, right? Like so many young people in America today. Anyway, and the other is a vector, and a vector has both direction and magnitude. Oh yeah. And you caught it. Okay. Anyway, that's despicable. I shouldn't use that joke. All right. Anyway, dumb movie. My bad. But anyway, so a vector. Yes, so we said that if we were to account for the direction, though, right? It's not just that I go a certain speed to Audrey's desk. For instance, I get myself out of the way so I can go in a straight line. I go very, very slowly. It's the walk of doom. Audrey, where is your homework? And she passes out, and I look at her empty notebook. Oh, versus, well, that I could take not just the speed at which I travel, but I could go for a particular direction. Let's see, I believe that's north, so that would be kind of a southeasterly direction, okay? I could account for direction if I wanted to as well. Now, speed in a particular direction, Michael, we call velocity. We oftentimes will use the terms interchangeably, but velocity accounts for direction. Now, I said we won't always necessarily do like a north, south, east, west. I could just say that walking to Audrey is a positive direction. So I walk to Audrey, that's positive. How do I show that my direction is the opposite as I walk away from Audrey? Class? Negative. So a lot of times we'll just use positive and negative to show direction. Positive meaning intended action, negative meaning the opposite of intended action. So for instance, if I'm walking toward Audrey and Audrey's like, I don't want him to check my homework. She chucks her highlighter at me, which would be a big mistake. But if she did, okay, she's not that dumb. That's why I use her in the illustration. Just picking on Michael now. But anyway, if she checked the highlighter at me, well, I'm going this way. If that's a positive direction, then the flight of the highlighter would be in a negative direction because it's in the opposite direction. Now, obviously, that's limited to just vectors that are along the same line with each other, right? If she's like, I don't want him to come, and she chucks a highlighter out the window. Okay, the window's not in this line, so how do we show the direction of the highlighter? It gets its own positive direction, I guess. Anyway, but yeah, speed in a particular direction we call velocity. And I said another way we can look at velocity then is because it's going to be in a straight line path, at least we assume it is. Even if I did walk all the way around the room to Audrey, velocity is only concerned with where did I start, where did I end up? What is that straight line distance? So it might as well be in a straight line. Even if it wasn't, that's what we're going to assume. How else could we define velocity then? Not distance over time, class, but displacement over time. So velocity, a couple definitions. First of all, for velocity, we could define it, as I said, speed in a particular direction, but also displacement per unit time. Now, technically, as I'm walking to Audrey, I'd be like, hey, Audrey. Oh, you don't have your homework, do you? And I could change my velocity as I'm walking to her, right? But if all I'm looking at is the, poor Audrey, but if all I'm looking at is the displacement from me to in front of her desk, and I'm looking at how much time it takes, that doesn't account necessarily for the fact that I may be walking at a constant velocity or perhaps at a variable velocity. We just kind of take the total displacement divided by the total time it took, class, which gives us what we call average velocity. And so in equation form, and I believe, check your notes, you have this equation, V sub AV equals D over T. I should have gotten this in our notes in our last lesson there. Our math used this in one problem and then not in the other one. So let's take a look at problem 1 and read that for us if you would. Audrey.
An airplane travels at a speed of 500 miles an hour. Express its speed in feet per second, being kilometers per hour, and meters per second.
There we go. Again, it's just a speed of 500 miles per hour. We don't care about the direction the plane is traveling. So it just wants us to change up the units here, basically. And this is kind of practice from chapter 1, right? What do we do, class? That thing, yeah, with the ratios, right? What do you call it? Dimensional analysis. Dimensional analysis. That's really all we're doing, right? So we'll take the 500 miles, put that over 1 hour, right? So 500 miles per hour. And if I want, let's say feet per second to be the easiest one. So let's go to feet per second. What's a ratio we'll multiply by here? Michael?
5,280 feet per
All right, and that'll cancel away the miles. And then, Kendall, we have feet per hour. I want feet per second.
You can do 1 hour equals.
Or 1 hour over.
Oh yeah, 3,600 seconds.
There we go. And that'll cancel away the hours. And check your work here. Should have multiplied for part A. 500,000. And what do we get for the feet per second? Back to Audrey.
733.
There we go. And is that 3 sig figs? Yes, so 733 rounded off, 733.3 repeating feet per second. Now I'm actually going to do part C next, because I feel like part C is the easier one to get next, and that's the meters per second. What would I have to do next, Audrey, to go to meters per second? I've got feet per second already up here. I want meters per second. Now what? Okay, so got my feet up here in the top.
Yeah, so you put 1 foot equals
Help?
3.281 meters over.
That's a meter right there. That's a foot.
1 meter over 3.281.
There we go. Put the meter over 3.281 feet, and that'll allow the feet to cancel away. So basically just divide what you have by the 3.281. We get about how many meters per second, anyone?
223.
About 223, around 224 if we're going 3 sig figs. Again, the 5,280 is a definition. The 3,600 seconds is a definition. This was 500.3 sig figs. This is 3.2814 sig figs, so we'll stay with the 3. And then I'm going to go back now that I've got this, and I'll go back and hit the kilometers per hour. Because basically, if I just take that ratio out, I've got my meters per hour. And then to go from a meter to a kilometer, what does kilo mean? 1,000. Because, so we know, Kendall, that a
meter is 1,000 fifty. No.
Other way around.
Other way around. 1 kilometer equals 1,000 meters.
There we go. So I can put my 1,000 meters down here and my kilometer up here, and that'll allow me to have kilometers per hour. So we could kind of re-enter that, the 500 times the 5,280. Divide that by the 1,000 and divide by the 3.281. And how many kilometers per hour, anyone? Again, that's a definition of a kilometer, so that's not sig figs there.
805.
About 805 kilometers per hour. So I went a little out of order here, but there's our 3 answers for number 1. How'd we do on number 1? Questions on number 1? All right, go and take a look at number 4 and read that for us if you would, Michael.
You walk at a rate of 1.34 meters per second for 30 minutes and walk 3.22 kilometers for 45 minutes, all in a straight line. What is your average velocity in meters per second and miles per hour?
Okay, so you go for a walk, and you walk a little bit, and then you walk some more for a little bit. So it says the first phase of the journey from here to here, walking in a straight line the whole time because why not? You walk for 30 minutes, class, that's a measure of time. And you go at a rate, it says, of 1.34 meters per second. Well, that's a positive 1.34 meters per second, class. That's our what, meters per second. That's a velocity. We think of a speed, but we're going to say it's a velocity because the positive indicates here. And so what we need then, if I know velocity in time, or we could say average velocity, because it's unlikely we're going 1.34 meters per second the entire way. Very probably there's a little variance there, right? But the average velocity here, if I know the average velocity and I know the time, what could I easily calculate? The displacement. How would I find displacement given average velocity and time, Michael?
Multiply them.
Yeah, just multiply them together, right? If you think of that as over 1, we're cross multiplying essentially, except I got a little problem here with my units. Thoughts?
Change it to seconds.
Yeah, if this is meters per second, then this has to be in seconds. So we're going to change 30 minutes into how many seconds, anyone? 1,800 seconds, right? 1,800 seconds. And if we just multiply those, it'll tell us how far we got during that amount of time. So how far did we got? 2,412 meters. All right, then we keep walking. And we walk some more. And for the second part of the walk, back to Michael, it says we walked
3.22 kilometers.
And it says in
45 minutes.
45 minutes. And we could, if we wanted to, find the average velocity for this part of the journey. But I don't actually care about that, because what it wants is the average velocity for the entire walk, right? And to find average velocity, class, I need two things. The total displacement over the total time. Well, the total time is 75 minutes, but that doesn't really help me, does it? No. 45 minutes becomes what, anyone? 2,700 seconds. So the total time traveled walking the first part of the walk and the second part of the walk, class, comes to 4,500 seconds spent traveling. And then the total distance, well, here I've got 2,412 meters. Here I've got 3.22 kilometers. Let's change the 3.22 kilometers, go kilo to unit. 3,220, right? Move the decimal 3 places. So what's the total distance traveled, or total displacement, I should say, since it's in a straight line?
5,632.
And so now that I know total displacement, I know total time, I can find average velocity. And what is this average velocity? Anyone? Yeah, 1.251, but we're looking here, I've got 2 sig figs from the 30 minutes. So we're going to say 1.3, now notice the units, meters per second. By the way, I don't know if I had you put that in your notes in our last lesson. Make sure you note the velocity is normally going to be meters per second. I think you have that, don't you? I think it said meters per second or feet per second if we're doing US customary, and then it said miles per hour is another way we'll think of it a lot of times, though it's not necessarily a scientific unit. And in fact, that's what it asks for. It says find it first of all in meters per second, then it says get the answer in miles per hour. So we're going to come back to this original meters per second here, and if we want to convert it into miles per hour, more dimensional analysis, right? Give me a ratio to multiply by, Audrey. So all right, then what, Kendall?
1 mile equals 5,280 feet.
All right, and then finally, Michael.
3,600 seconds over 1.
All right, so we'll take the value on the calculator if you were just doing it. It's the 1.251555555, multiply by the 3.281, multiply by the 3,600, and then just divide out the 5,280. And how many miles per hour? Do we have here?
2.80.
Yeah, well, going 2 sig figs, we'll just say 2.8. So 2.8 miles per hour. Notice it's a little more than double the meters per second. Okay, so that's kind of a rough thing that you'll see me use from time to time as we work a problem that's in meters per second. I'll usually tell you approximately what it is in miles per hour, and all I'm really doing is doubling and then a little bit more. Okay, so You'll see that as we go through. Questions on problems 1A and 4. Did any of you have these answers for number 4? Do you see the thought that would work into it? You need total distance and total time. Well, total time they gave me, 75 minutes. Convert that to seconds. They didn't give us total distance. That's why we had to find this distance first. We already knew that distance. Now, so there we have our total distance. Make sense? Or displacement, I should say. Look at problem number 5. Kendall, read that one for us.
How long does it take a train moving at 20 meters per second to cross completely a trestle 75 meters long if the train is 335 meters long?
All right. How many know what a trestle is? A trestle. Nobody? It's a train bridge. So like we call something a bridge if cars drive on it or people walk on it. And if a train goes on it, it's called a trestle. Why does it get a fancy name? I don't know. Maybe just to specify that's for trains, so don't walk on it or drive on it. I don't know. Anyway, so for instance, this is a really long bridge. 75 meters, that's actually not that far. Maybe across the Chattahoochee, right? There's a train bridge. How many have walked near or under the train bridge across the Chattahoochee? The river walk on both sides, so we've been on both sides of it. If a train's going over, I don't recommend you stand underneath, right? Stand back a little ways. Just a recommendation, of course. Keep my kids back, but it's fun to watch the train go by. It's loud. Chloe doesn't enjoy it as much. Anyway, so we've got, for whatever reason, we've got something here. Maybe it's water, and then we've got something here, and here's train trestle, okay, any supports and whatnot. And the choo-choo train comes here, and old-style choo-choo train, okay? And it's got car after car after car after car. They have no wheels, okay? And the train has to get across. Now, the train itself, it says, is, Kendall?
335 meters.
335 meters, and the trestle is
75 meters.
75 meters. Now, the key word here is completely cross, right? Because the train is not crossed when the engine goes 75 meters, right? We still have the back of the train to get to. So what is the actual displacement needed here? Anyone?
410.
The total displacement we need here is 410 meters. Make sense? And the train is moving at a constant rate of 20 meters per second. Class, that 20.0 meters per second is the velocity, the average velocity. Now here, when we add 335 plus 75, place value is the units digit. That means our decimal, if you will, would go here. So as we do our calculation here to find how long it would take, class, that's finding time, right? That's finding our time here. How do I solve for something in the denominator again? Alternate and divide. So at your seats, find how long it takes our train to completely cross the trestle. And looking like we're going with 3 sig figs, which works out great for us. Ken, do we get?
24 minutes.
So notice I've got meters per second here. When I've got meters here, and when we alternate, I've got meters per second here. So the meters are going to cancel. Notice per second is a denominator of a denominator, so it flips to become the numerator, so just seconds. There we go. So that's not long at all, right? 20.5 seconds for this train. That's a pretty long train to go completely across the trestle, and it's gone. That's really moving, though. I mean, again, that's 45 to 50 miles an hour. Okay, the train going across the trestle, across the Chattahoochee, not going that fast, okay? So you get a longer show if you're a little kid standing there watching. And anyway, but the other moral of the story is if train is moving fast, don't park on tracks, right? How many saw on the news this past weekend, trying to remember where it was, but a police officer made a traffic stop and he parked his cop car on the tracks. Where he pulled over the lady, she was drugs or something, pulled her over, and when he pulled up behind her, he happened to park his car on the railroad tracks. Well, he arrested her, handcuffed her, put her in the back of the car, and went to search the car, and a train came by and obliterated that police car. It was awful. And again, he's responsible for her safety because he's arrested her. She's under his care and custody. Really bad situation for the officer, worse situation for the lady. And the takeaway from that is never park your car on the tracks. car battery dies, car stalls out, you're stuck there. There wasn't even time to get her out of the car. Like all of a sudden, it's just saw lights, heard train, and train was on him that fast. So anyway, really kind of horrifying video to watch on the news on Saturday morning. But anyway, there's a lesson to be learned in it, right? So those of you who drive, or do you drive yet? You drive, okay. So so don't park on tracks, stay back, or get across, but don't ever stop on tracks. Anyway, train moving fast. Questions? All right, next thing in your notes. And we know this. We've been in all these problems assuming what we call a uniform velocity, or we've just gone to the average velocity, since, velocity does change, right? And we have a word for a change of velocity. Now, for instance, Audrey, you got to watch this when we did our last endurance run, right? The kids running around, I say running, the kids start walking, and they walk, and then it's usually the guys, right? The guy is walking his endurance run, and all of a sudden, he comes near where the girls are, and he starts going very quickly. Do you need tissue?
There's something in my eye.
I was about to say, go ahead and take care of your eye. Pretty obviously, your eye is in distress there. And all of a sudden, he starts running, right? He speeds up, his velocity changes, right? And then once he gets out of the range where the girls would be watching him, he starts walking again, the slob. And so there's this increase and decrease in velocity, right? You also know this, for instance, when you back out of your driveway and you get ready, or maybe you pull up to a turn and you wait your turn and finally there's a gap and you pull out into traffic and you can speed up, right? And I'll be honest, Kendall, do you have a lead foot like that, or are you more the, yeah, that's you, okay. I was in traffic last night coming home from church, and there was this really cool sports car behind me, and I could tell he did not want to be behind me. He wasn't being overly rude about it, like being right up on my tail, but like, he didn't want to be behind me. We finally got out of the merge lane. Of course, I start speeding up like you're supposed to do, right? That's why the ramp is there. It's an acceleration lane, right? Get up to speed. So I was already going 70 by the time I got into my lane, because of course I was going 65. I'm pretty sure it was 65 as I got in. Well, anyway, he jumped out, and his change in velocity was greater than mine, right? Now, he also got up to a higher speed than I did, and he got up to speed quicker than I did. I'm in a Honda CR-V. It's a crossover. It's not, a sporty thing or anything. He definitely did, and he wanted to show off and show me that his car could get up to speed faster. So it's not necessarily even just the amount of change in velocity, but how rapidly a change in velocity can happen. Or for instance, if you see something ahead of you and you have to slow down, right? There's, slowing down and there's jamming on the brakes, right? Well, you change velocity both ways, just one changes your velocity more quickly, right? A change in velocity based on the amount of time it takes to change is called acceleration. Acceleration. So, those sports cars that do 0 to 60 in 5 seconds versus the old jalopy, the old Mercury, let's just throw a random brand out there, that does 0 to 60 in, say, 5 minutes, okay? They both get to 60. I'm just picking on your car now. Just one gets to 60 more quickly than the other one, right? It doesn't really take 5 minutes, does it? You've got a good little car there, don't you? Anyway, right, it depends on how much time it takes to get up to speed. So acceleration is change in velocity per unit time. Change in velocity per unit time. We're concerned not with just how much does the velocity change, but how rapidly does it change, or the rate of change, we might say. In equation form, we could say this. We'll represent acceleration with the lowercase letter a. If velocity changes, that means there is some velocity when you start out, and there is some velocity at which you end up, correct? And if we were to subtract your starting velocity, for instance, suppose that car behind me, I was going about 45, 50 around, on the ramp until we got past the windy part and we could finally start to accelerate. And so I went from about 50 to about 70. Probably took me about 4 or 5 seconds to get up to speed. He went from 45, 50 or whatever behind me. He got up to 70 in about 2 seconds. And so he jumped all the way across the lanes of traffic to the far lane where he could go nice and fast, he thought. I just thought it would have been cool if there was a police officer just waiting right there. That's the best. Or my favorite is you're driving down like a 2-lane highway, with the dotted yellow, and this person's like sitting right on your tail the whole time while cars are coming, and finally there's a gap on the other side, and they race around you, and like half a mile down the road, they whip into McDonald's. You really want that greasy hamburger that bad, don't you? It's like burned all that extra gas and whatever, you know. Anyway, impatient people. But there's an initial velocity starting out. There's a final velocity. If we subtract the final velocity minus the initial velocity, that gives us our change in velocity, we said, per unit time. So here's your second equation for this chapter. A is equal to v sub f minus v sub I over t. It's the definition of acceleration in equation form. Change in velocity per unit time. There's our equation for acceleration. Now again, you know this because you drive, right? You push on the gas a little bit and it responds a little bit. You push on it more, it responds a lot more, and then back off a little bit, right? But imagining if you just kept a constant pressure and the gear ratio didn't change, stayed in the same gear, right? So just a nice steady increase in speed the whole time, right? It doesn't usually happen that way. How many, you see your tachometer like spike at like, 5,000 RPMs, you're like, well, I just wasted a gallon of gas. It's not quite that much, but you get the idea, right? Or in your case, 2 or 3 gallons of gas. That one time it spikes in the Suburban, right? Yeah. But right now it's like, man, there goes $8. But anyway, but if you could keep a nice steady pressure and it didn't spike on the tachometer as it tried to shift gears or anything like that, just nice, easy progression, we would have a constant or what's called a uniform acceleration. Realistically, most acceleration is variable. We're going to assume uniform acceleration only because you would need calculus to find variable, and it would have to be defined by a function, and we don't have any of that. So we're assuming uniform acceleration in this class. We're going to assume it's a nice steady rate from whatever speed you start out to whatever speed or velocity rather you end up, subtract to get the difference, divide by the time it took to get from one speed or velocity to the other. Now, it is possible, isn't it, that you start out faster than you end up, right? This is pulling into your driveway, right? Use the middle pedal, not the one on the right as you pull in, correct? Otherwise, bad day, garage door doesn't hold up, parents mad, car slightly dinged, garage door wrecked, okay? But hopefully, right, as you pull into your garage, right, your initial velocity as you come toward the garage is greater than your final velocity because you should be slowing down, right? Well, think about it. If you take a small number minus a big number, small minus big always produces what? A negative, right? So if your initial velocity is greater than final velocity, acceleration is going to be negative. And we call this negative acceleration deceleration. This negative acceleration is called deceleration. So speeding up we generally refer to as acceleration. Technically, slowing down is a form of acceleration, but we give it its own name, deceleration. So as you're driving down the highway, you're like, okay, this is my exit. Once you get off on the exit, then you take your foot off the gas and slow down, yes? Not half a mile before the exit. Once you reach, this is life lesson if you're watching on YouTube. Once you get to the exit, take the foot off the gas, and if necessary, since we have some really weird exits here in Columbus, with very short deceleration lanes before they do a really hard turn, maybe you also use the brake, but that's once you get into the deceleration lane. Of course, the opposite is true. When you get onto when you're about to get onto the interstate, whatever ramp you have, that is for acceleration and getting up to speed. So if everyone else is going 65, okay, they're all going 75. If they're all going 75, you're going 75 by the time you merge. You don't come in at 50 and make everybody behind you slam on their brakes, right? Right? This is good driving tips in physics class. All right, anyway, questions on acceleration, deceleration. All right, we got some passionate people in here who strongly concur with me. This is good. This is good. Look at page 86. Look at page 86. I gotta move quickly. It's been too long giving driving tips. Page 86, look at the example problem, rather, about acceleration at the very bottom of page 86. And Michael, you've got little sisters. You read this one.
A boy chasing his little sister down a hill at 2.38 meters per second suddenly fell and started rolling. If he rolled it for 4.91 seconds and his final velocity was 5.26 meters at the base of the hill before sliding into a puddle.
What was his acceleration? He got lost at the puddle. He's like, I'm done. All right, so I don't know, maybe this is Michael in his roly-poly days. And which little sister might this be?
This would probably be Elizabeth.
Elizabeth. You would chase Elizabeth, no, not so much Abby.
No.
No, because Abby's in there reading a book anyway. What's the fun? Elizabeth's out there playing and doing things actively and whatnot. Anyway, so that's not to say that reading books isn't good. For the record, Grace Christian School recommends reading of books and gaining of knowledge. Anyway, so he's running 2.38 meters per second, and rumble, tumble, 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 tumble. He gets faster and faster and faster as splash. All right, and right before splash, it's 5.26 meters per second. Okay, so we have an initial velocity, we have a final velocity. Class, if we subtract, we get the change in velocity. What is the change in velocity for a little boy? This is Michael's younger days, by the way. He's not really pulling anymore. So what is the change in velocity? Well, that's definition pretty good time. Like, actually, what is it? Plug in the numbers. Calculator. What's the change in velocity?
Negative 0.5865.
Oh, he started at 2.38, tripped and and he's 5.26. All right, we subtract those.
2.88.
Who?
2.88.
2.88. Y'all got the same thing, 2.88 meters per second. All right, that's the change in velocity. And how much time did he tumble, 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 speeding up as he tumbles?
4.91 seconds.
4.91 seconds of tumblage. All right? Now notice what's going to go on with the units here. The meters per second gets divided by yet another second. That's 2 seconds that have been divided. Notice my answer is going to be in meters per second squared. Put that in your notes. Meters per second squared is the most common unit for acceleration. US, we'd say feet per second squared. Most of our problems, we're just going to use the SI anyway. So meters per second squared here. And we need to divide that out. The 2.88 divided by the 4.91, we get how many meters per second squared? Class? 0.58. 65, blah, blah, blah. And they gave us 3 sig figs, 3 sig figs, 3 sig figs. So yes, we will round off to the 3 sig figs, 0.587 meters per second squared. And there we go. By the way, you recognize meters per second squared, right? Gravity, we said 9.80 meters per second squared. It's an acceleration, so things that fall get faster and faster and faster and faster. We're going to talk about that in a couple of lessons, but that's that G value. It's a form of acceleration. Questions on that? All right, look at example 6.4. And none of you have snow anyway, so let's go with, pretend it's Peter. Kendall, read this one for us.
A boy on his sled pushes off.
I just said it's Peter, and then look right at Audrey and say Kendall. Oh, go ahead, Kendall. We'll pretend it's Nathan.
That's not good.
Hey, he scored a touchdown. Don't knock it, okay? A boy who can score a touchdown, he can go down a sled.
Yeah.
Go on a sled. Down it.
A boy on his sled pushes off from the top of a hill at a velocity of 3.0 meters per second. If he accelerates at 0.50 meters per second squared, what is his velocity after 8.0 seconds? What is his average velocity?
All right, now he starts off, right, as he pushes off on the sled, he pushes off, and he starts out at 3, but because he's going down a hill, right, gravity's pulling him, he's going to be getting faster and faster as he goes down. It's not a free fall, so we can't use the 9.8 as his acceleration. It says instead he accelerates at 0.5 meter per second squared. How fast will he be going? Do you see that what we're looking for here is his final velocity? So we know the acceleration, we know how fast he starts off, and we know how long he goes down the hill, or at least for this amount of time. It says after 8 seconds, how fast is he going? We need the final velocity by itself. So we need to solve this for the V sub F. How do I get it by itself? Kendall? Start by getting rid of the...
V sub I.
Well, that's grouped though. Remember the fraction bar is a grouping symbol. So since it's grouped, it's actually more attached than the t. So get rid of the t first by multiplying it to get at, right? And of course t's cancel here equals the vf minus vi. And then finally just
add the v sub I.
Right, move it over to this side, right? Add it over to the other side. So, with his initial velocity, started off class going 3 meters per second, and then he accelerates, it was half a meter per second squared for 8 seconds. Well, we need to multiply the 8 times the 0.5, 4, and then we'll add that extra 4 meters per second onto the 3 meters per second to get class? 7 meters per second. Questions on the first part there? Do you see how they got to what we got to? Make sense? Then the next part says, what's his average velocity? Well, if he starts off going 3 meters per second, and he ends up at 7 meters per second, what would be the average? 5, right? Average is just add them and divide by 2. And of course, they worked a separate equation for that, which is really annoying. I would look at the first part there, just add them, divide by 2, take half as it shows there. Questions on that? Turn over to page 93. Page 93. And take a look at problem number 10. Problem number 10. Go ahead and read that for us. This time, Audrey.
If an object is accelerating from rest to 50 meters per second in 15 seconds, what is its acceleration?
All right. So this time we're just looking for acceleration. What's my equation for acceleration? Audrey?
A equals B, so that minus B, so that over T.
There we go. And it says a car is accelerated, or an object, excuse me, is accelerated from rest. What does that mean?
It wasn't moving.
It wasn't moving. So from rest means, class, that the initial velocity is 0. Well, basically then we don't need to worry about it because something minus 0 is itself. It says it gets up to a rate of 50 meters per second. And that's about 110-ish miles an hour. So this thing's moving whatever it is. And it takes how long to get up to that rate? 15 seconds to go that fast. It says what's the acceleration? Well, pretty straightforward. Class will just divide. And what do we get here?
3.3.
Good, 3.3 repeating, but I think it's just the 2 sig figs. So we'll say 3.3. Now again, what are the units for acceleration? Meters per second squared. So velocity, class, is meters per second, and the acceleration is the meters per second squared. All right, well, we are out of time for more, so we'll have to save those other couple problems we were going to do, save those for tomorrow. For homework this evening, you're going to complete a handout. So if you're watching on YouTube, it's in the description of the video as usual. Complete a handout. On the back of the handout, though, I want you to copy some equations from your textbook. So homework is to complete a handout and then read pages 87 to 89. Read pages 87 to 89. On page 88, there is a table of equations, table 6.3. I want you to copy that table 3 times on the back of the handout. Okay, so complete the handout, read pages 87 to 89, and on the back of the handout, copy page 88, table 6.3, 3 times. These are going to be some equations you're going to need to have memorized really well that we'll be using throughout the rest of this chapter. All right, you are dismissed. Have a wonderful rest of your day and drive well.